Math 1314, Tyler Junior College, Section 5.1, 2x2 linear systems of equations. Solving a 2x2 system by substitution. In the previous video, we discussed how to solve a 2x2 system of equations by graphing. You simply graph each line, and the intersection point represents the solution. But the problems with that were twofold. Number one, you have to graph the lines, and number two, you better hope you can see exactly where they intersect, because if it's not an integer pair, or if either the x or the y is a fraction or a decimal, good luck eyeballing that value. So nice in theory, but without technology to correctly identify the intersection point, I would not solve the system by graphing. However, we can solve by substitution. The premise behind substitution is pretty straightforward. This is another example of problem-solving strategies in general. Our goal is to figure out what x equals and what y equals. But our problem is we have too many variables at one time. For example, if we were to pick the first equation, x plus 2y equals 3, we can solve for one variable, but the other variable will be trapped on the other side. I could solve the first equation for x easily, and I could solve the first equation for y, but neither one of those approaches would tell us what x equals or y equals numerically. So we have too many variables at once. That's the obstacle we have to overcome. There's a couple of ways to overcome too many variables at once. One way to overcome it is to use a substitution, where we rename one variable with something that it equals, and after that, we're down to one variable. How does substitution work? Well, it's pretty straightforward. Let's go ahead and build a list titled How to Solve by Substitution. If you want a more descriptive title, How to Solve a 2x2 linear system of equations by substitution. Number one, and you have to make some decisions here. Isolate either variable in either equation. This is your substitution. So you have a decision to make. Pick a letter and get it by itself. And in a 2x2 system, you normally have four options. First x, first y, second x, or second y. Sometimes there's a clear-cut choice as to which is the best option. Which of these four variables is going to be easiest to isolate? The first x. Why? Its coefficient is 1. If the coefficient is 1, I don't actually have to do a division move, as opposed to, say, the second x. If I were to solve for it to create my substitution, my last move would be to divide everything by 3. But a quick glance across the rest of the equation shows you that nothing else wants to divide by 3. That doesn't mean you can't do it. That just means you would create fractions, possibly unnecessarily. So when you're isolating any variable, I'm going to put an asterisk on this. I really don't have room down here to define the asterisk, so I'll do it over here. If possible, comma, choose a variable whose coefficient is 1 or -1. If it's -1, then we have to divide everything by -1 at some point, but if you're an integer and I divide you by -1, you'll still be an integer. All right, so let's make our substitution. We're going to isolate this first x, and you can just think this out. What does this imply? If we isolated the x by moving the 2y from the left to the right, then the 2y would change signs. Technically, the move that you're doing is subtracting 2y from both sides. But the net result of that move is you get x equals -2y plus 3. This is our substitution. What a substitution says is one letter equals another expression. X is equal to -2y plus 3. And what that gives you the license to do is to replace any x anywhere in the system with what it equals, in this case, negative 2y plus 3. Our second step, use the substitution to rename a variable in the other equation. Emphasis on the word other equation. And just as a casual reminder or warning, you want to use parentheses. Allow me to demonstrate. The purpose of this substitution is to take out an x and replace it with negative 2y plus 3. So we're going to take this equation and we're going to take out the x and replace it with negative 2y plus 3. But before you do that, I recommend changing the x to empty parentheses. You know, this is a gimmick I use quite often, especially when you substitute a larger expression for a single variable. Remove the variable, replace it with empty parentheses, then substitute what it equals. In this case, x is equal to negative 2y plus 3, so inside the parentheses that replace the x, I'm going to put negative 2y plus 3. The main reason, if there's a coefficient in front of the letter that you're replacing, it's going to get distributed, and the parentheses help remind you of that. At this point, notice where we are. We have one equation with one variable. Granted, the variable shows up twice. The only variable in this equation is y. Once you get it down to a one-by-one system, you should be able to solve. Your third step is to solve for the remaining variable. So we're going to solve for y. Let's see, first we'll need to distribute the 3 to get negative 6y plus 9, and then minus 4y is equal to 19. We have a couple of y terms we should combine. Negative 6y and negative 4y is negative 10y. And by the way, if your instinct is to do something like this, stop. I understand the motivation behind adding 6y to cancel the minus 6y. But do you see the problem with this move? To keep an equation balanced, whatever you do on the left side of the equal sign, you also have to do on the right side of the equal sign. I just did the same move twice on the same side. I see people do that all the time. Don't be one of them. The time for doing this is when you have variables on opposite sides and you need to get rid of one of them. If they are on the same side, just combine them. Negative 6y, negative 4y is negative 10y. We still have the plus 9 equal to 19. All right, we're 2 shots away. I'll just describe what happens next. Subtract 9 from both sides. You get negative 10y on the left, but you get 10 on the right. And when you divide both sides by negative 10, you get y equals negative 1. Hooray, we have our solution. No. We have half of our solution. We know what y equals, but we also need to know what x equals. How are we going to find the value of x? By taking advantage of what we know. We know what y equals, and we have not one but 3 relationships between x and y. You could argue that the first is the same as the substitution because it is, but we have a variety of places to help us find the x. I would recommend using the substitution. Why? We want to know what x equals, and the substitution starts out by saying x equals. For our fourth step, substitute the known value. Substitute the known value, we know what y equals now, into any equation to find the unknown value. So stick the y somewhere and solve for x. If we were to do that, we can pick any equation, either the first 2 or the substitution. I'm going to use the substitution because I want to know what x equals, and it says x equals. Don't get me wrong, any of them would work if this is the correct y value. If we substitute -1 for the y in the substitution, we get x equals -2 times -1 plus 3. And now we just have to follow the order of operations. -2 times -1 is 2. 2 plus 3 is 5. The solution to the system, the x is 5. The y is -1. Shouldn't surprise you. Never mind. I thought this was the previous example. It's not. If we were to graph these lines, they would intersect at 5, -1. And that's how you solve this 2x2 system by substitution. It's 4 straightforward steps. Isolate, create your substitution, use the substitution, solve, substitute, and solve. Of course, there's a big caveat in the asterisk. If possible, choose a variable whose coefficient is 1 or -1, which clearly raises the question, what if none of the variables have a coefficient of 1 or -1? I'll demonstrate another example in the next video where that happens to show you that the technique will work always.